Greetings, fellow graphics nerds. Today I want to talk about the heat method, which is a very neat algorithm to find distances on the surface of a mesh. It was published in 2013 by Dr. Keenan Crane and his team, and I find it to be a very neat application of mathematics, which is one of the reasons why I like the paper so much. So without further ado, let me actually talk about the paper. The first thing is most of you are probably looking at this gray rabbit and wondering what is this all about, like why should I care about these images? So let me explain the general idea of what we're trying to accomplish. What the heat method tries to do is it tries to find geodesics on the surface of a mesh. A geodesic is the shortest line between 2 points, but it's not the shortest line in Euclidean space, it's the shortest point on the actual surface. So for example, if you see this point over here on the tip of the ear, the distance that we care about is the shortest distance that you can travel through the surface all the way to the back. So it like goes through the neck and then up the ear and then to the tip. So in this particular example, what you're looking at is a visual representation of the distances, where the farther away from the source a point is, the more white it is, and the closer it is, the darker it is. So in this example, the ears are, for example, farther away from the back than, say, the neck or the head. And as you can see, the image that is getting generated is conformal to what we would expect if there was a source point on the back of the rabbit and all other points are getting their distances calculated relative to that point. So this is more or less what you can see if you just want to render it, but of course this is something that most of the time you're not going to use for rendering directly. This can be used for physics simulations, it can be used for mesh editing, it can be used for mesh UV mapping, it can be... Essentially there's a bunch of really neat applications that you can have for geodesics. So yeah, let me go to my tablet and give you a quick overview of how the method actually works. Okay, so the first thing is, although I understand the paper well enough to actually implement it and tell you how to implement it, the paper is based on a technique that is very common in scientific computations called FEM, which stands for finite element methods. The general idea is that you discretize a continuous medium and you do discrete calculus on that discretization in order to try to approximate a more complex continuous problem. Now, I'm not going to delve too much into that because I am not an expert on it. I am aware of it. This is just to give you pointers if you want to go more in depth into it. Now, about the heat method specifically, you don't have to be particularly knowledgeable about any of this to understand the general idea. Imagine that we have our mesh. So we have our rabbit mesh, our beautifully drawn, perfectly and true to the source representation of the Stanford rabbit. Now, what we're gonna do is imagine that we have an infinitely thin needle that is also infinitely hot, and we are going to touch the rabbit with this needle. Now, if we assume that only the surface of the rabbit exists and that everything else is vacuum, so essentially inside of it it's completely hollow, and outside of it there's no atmosphere, there's no air, there's nothing that can transport energy, well, what's going to happen is that the energy from the needle is going to slowly diffuse around that point where you're touching the rabbit, and it's going to do so around the surface, right? So heat is essentially going to be irradiating from that touching point to the rest of the mesh over time. And what's going to happen is, because nature tends to always follow the path of least resistance, this diffusion is going to always follow the shortest path on that surface. That shortest path is the geodesic, which means that if we wait for a couple of moments, like less than a microsecond, just some instance, some non-zero time, the heat that gets dispersed through the mesh will have reached every single point. So essentially heat will have traveled all through our mesh to every single point, and it will have done so following the path of least resistance, which also means that points that are hotter are going to be closer to the source of the touch, and points that are cooler are going to be farther away, because over time more energy has been dispersed around the touching point than to the rest of the mesh, right? For obvious reasons, the flux of energy has just had more time to pass through those points than through the points that are farther away. So this is the main intuition behind the heat method, that geodesics and heat diffusion are essentially the same problem, or rather that heat diffusion always occurs along geodesic lines. Now, from here on, the next step that the paper does is it first models the heat diffusion as I just described it. It is going to do that point diffusion thingy, and the heat is going to radiate, and now we have a mesh where at every point we have a heat value. Now let me draw the rabbit again. Yes, you can all tell I am a beautiful artist. On any case, so now we have this mesh, and at every point there is a heat value associated to it. The next thing that we are going to do is we're going to get the gradient, the discretized mesh gradient of this mesh. So the gradient in this particular scenario is going to look sort of like this for the region that is close to the point, and then for example here at the neck it would be something like this, and then at the ears it would be like this, so on, so on, so on. Basically at every point you have the direction that locally maximizes heat flux. That is essentially what the gradient is. So after we calculate this gradient, which is actually a very simple subroutine to code, it doesn't require that much code. You can do it in probably like 20 lines, 30 lines. It's very straightforward once you have a mesh representation, such as a half edge. Once you have this gradient, the first thing that you're going to do is you're going to flip it, and you're going to normalize every single line. So instead of each arrow pointing in the direction that I just drew, like this one for example would be pointing in this direction, this one now instead is pointing in that direction, this one is going to point in that direction, you get the idea. And you are going to normalize each vector, which means that you're going to disregard the norm and just going to set it to 1. Now, once you have that, what you should obtain is something like this. Now, what you should obtain is something along the following lines. Now, every point, instead of looking towards the heat source, is pointing away from it. And what is very important is that it's locally pointing in the geodesic direction. That is to say, if I have this vector over here, and that vector is the reverse normalized gradient of the heat diffusion, then if there is a geodesic going from here and passing to that point, this gradient vector, this normalized and flipped gradient vector over here, is pointing in the direction of that geodesic line. And a very important theorem from differential geometry tells you that every geodesic in any mesh, in any manifold, can be uniquely identified by a point and a direction vector. In other words, since we have the point and we have the line, we know at that point exactly which geodesic we're talking about. Once you have these, what you can do is you can integrate the gradient over the surface, and when you integrate the gradient, that is going to give you the actual geodesic length at that point. Now, this is the high level overview. I am about to go into a little bit more detail. These were just the diagrams that I wanted you to have in mind to kind of understand the code that I am about to show you. So, the prior was the high level overview of more or less what we're actually trying to accomplish. I am also going to post the original paper and resources related to the theory behind it. I'm just going to walk you through my implementation of the algorithm so that you get an idea of how this would look like in your code. So we're going to need two matrices. One is going to be a diagonal matrix where the entries along the diagonal are the sum of the areas of the triangles incident at every point. So that may sound a little bit complicated. The idea is this is a diagonal matrix that has number of vertices by number of vertices dimensions, and then in the diagonal value I, so you know, if the left top corner is 0 and then the one that is down and to the right of that is 1 and the one that is down and to the right of that is 2, so on and so on and so on, so that every vertex has a diagonal entry associated to it. Well, every vertex has a bunch of triangles that it is connected to. You're just going to add the areas of these triangles and you're going to multiply that by 1/3. That's what this matrix is going to be. The next one is a little bit more complicated. It's the Laplace operator, the discrete Laplace operator. I am going to link the Wikipedia entry on it on the description. The discrete Laplace operator is a discretization of taking the gradient followed by the divergence of a given function. For now, for the purposes of this video, you can consider it as math wizardry because it's not hard to actually set it up, but I do encourage you to read not just the Wikipedia page, but any resource that you can get your hands on this, because it's a very important mathematical construct for solving a lot of physics and geometry problems. On any case, so we are just going to fill in the actual values of the Laplace operator. This is what this section is doing. It's not terribly complicated. Literally, it's just calculating exactly what the Laplace transform is supposed to be at every point. This is more clear if you actually see the mathematical definition, and it's just setting the values at each point. Now, after which we are going to fill in the values of that diagonal matrix, and that's it for this part. So all the way up to here, we're just doing the setup. All of this part is just filling in the values of the matrix, of the matrices. The next thing, and this is where the method actually starts, is we're going to solve the heat diffusion problem. The heat diffusion is that first step that I was describing when I was showing you the rabbit, where we have this source of heat that is starting to diffuse through the surface of the mesh. And at every point we're just calculating, okay, so after a short amount of time, in this case is going to be 0.01 units of time, this is how hot every point is going to be. So, you know, it's basically a linear system of equations, and if you are like me and you just want to leverage a pre-existing solver, it's very, very simple. Now, after this step, what we have is a vector that tells us at every point how hot that point is after a few seconds, a few microseconds, or a few instances of heat diffusing. After which we are going to get the gradient as I previously described, and once again the gradient function is not very complicated. Most of it is just grabbing the values that you actually need to calculate the gradient. So on it, now we get the gradient. After we get the gradient, what we want is to integrate the divergence of the gradient on the surface of the mesh, because that's what actually gives us the geodesic length. Now that may sound a little bit complicated. It's not that hard. If you see here, all of these is just grabbing values left and right of what we actually have to calculate. The actual calculation is just here, where we're just adding. This is essentially a discrete integral. It's a discretization of a continuous integral. We're just taking the divergence and adding it together, multiplied by a small coefficient relative to the angles of the triangle that it's incident in. That is a mouthful. Basically, we're just adding the magnitudes of the gradients together for all given purposes times the weight. And then once we have this, we are able to find the solution to the geodesic. Now there is a small catch, and that is the solution to the linear system of equations that we find after this step is true only up to a constant. So you might not actually get the actual geodesics, you might get the geodesics shifted by a number. And that was something that tricked me at the beginning, and I spent a few days trying to figure out what was wrong with my code or with my math. So basically you need to make sure that the smallest value after you solve this is 0, which is very straightforward. All that you're gonna do is you're gonna find that smallest value, and then you're going to subtract it to every other entry in your distances. And after you do this step, you're actually going to have the geodesic distances on the surface of your mesh. Now, if you made it this far, thank you very much for watching. This video was a little bit more challenging for me to do because this is a paper that I understand well enough to implement, but there is more work for me to do to understand all the theory of the mathematics that go behind it. Don't take this as a tutorial, don't take this as a class, take this as a motivating example. I implemented this. If you just need to implement it yourself and get it going, I showed you the code of how you can get it working, and I kind of try to convey as much of the theory as I understand as possible. I, however, acknowledge that my explanation might have had some holes in it, so I do encourage you to make use of the resources that I am going to put at the bottom of the video, such that you can better understand all of it. Don't just take this video as the only source of information. With that having been said, thank you very much to my one supporter on Patreon. Thank you very much for everybody that is watching these videos regularly. And yeah, I'll try to have a new video relatively soon. Bye bye.